Welcome back to Machine Learning's class. Today we're having the session 11. For people who are watching the video, you may be curious, where is our session 10? In fact, at session 10, the students had an in-class quiz. Then three students presented their case of how they applied the KNN method to predict handwritten digits. For all the three students who present their case, they were able to achieve an accuracy rate around 97% on their testing data. Really good job for all the three students who presented their job. Today, we're going to talk about neural network concepts. In fact, we're going to have two sessions to cover the neural net concepts. Some of them will be covered today, and some of them will be covered in our next session. Nowadays, when people talk about machine learning, oftentimes people actually talk about a neural network or deep learning algorithm. That's because the neural network or deep learning are achieving the best outcome across all the machine learning algorithms nowadays. In some cases, the machine learning based on deep learning are even exceed human performance by big margin. And here we just show a few successful applications in recent years for the deep learning cases. You can see they span from very different areas, such as speech to text, language translation, image recognition, robotics, or the medical cancer diagnosis, astronomy discovery, and arts. Here, if you go to the website, it's pretty good online summary where 30 amazing deep learning applications are listed. Now we understand neural network algorithm is very powerful, but why it is so powerful? Before answer that question, maybe let's think about how our brain works. Now, on this page, I have four pictures. And for humans, when we look at the pictures, we receive signals. Then it goes through some processing in our brain. Almost instantly, all of us can conclude all the four pictures we're seeing on the page are dogs. I don't think people will have difficulty doing this kind of recognition. It's pretty trivial effort for our human brains. Now the question is how our brain works. I do not have an exact answer. The whole thing is also under research currently. But what we can tell is we directly observe certain signals on previous page, such as color, shape, location, foreground, background, a lot of informations that are describable. That those signals go through the layers in our brain's neural network. Without knowing exactly how it works, it just works. And we can make instant conclusion that is all pictures include a dog. Even though we do not know exactly how the brain doing the work in our brain's neural network, but we can tell that is, we can feel that is when we make the conclusion, we do not really depend on single features such as color or shape or size, so on and so forth to make the conclusion. We kind of consider all the signals in certain integrated way. Then we make a holistic conclusion that each picture contains a dog. No matter it's a real dog, it's a color one, or it's a black, white, or could be just like silhouette, and or maybe just a cartoon. Anyway, our brain works very well and make such a conclusion at ease. So now let's think about if we want to build a model to predict an athlete's performance, and we may use the following inputs, observable inputs or features. Let's assume we can have certain measurement on each of the following features. So the first one we can consider is how tall an athlete is. The second one is how powerful the athlete is. And also can consider the flexibility, the speed, the agility, and the techniques and mental strength. Of course, this is a very short list, very simplified list. But let's assume we just consider this many 7 inputs for now. And you can also think about one sport that you are familiar with. It could be tennis or could be basketball or whatever sports you are most familiar with. In my case, I'm more familiar with tennis. Maybe I will relate the case to the tennis when I go through the following pages. So one thing you can also realize is when we consider the 7 inputs or 7 features, the overall performance, the overall how good an athlete is not really driven by each individual attributes, each individual feature, or maybe just simple linear combination of these features, because those features may have interaction. For instance, the performance we can think of as a product of physical capability, techniques, and mental strength, right? This is when we think about interaction. Another example is if you think about outputs of somebody's work, the output of somebody's work could be the productivity times the number of hours or number of minutes someone put into the work. Similar concept. Here, this may not be exact formula, but somehow we know that is the interaction, the combination of features decides the overall performance. In our case, the performance of athlete. If we go further into it, we also realize that is the physical capability, since we have multiple attributes are associated with physical capability, itself is also a combination of many multiple features we have in the list, like height, strength, flexibility, speed, and agility, so on and so forth. And furthermore, if we think about the height or speed, two specific features, we may also realize that each feature's contribution to the overall performance could have a nonlinear impact. Let's take height as example. So this chart is not based on any actual data or very concrete quantitative analysis. I would say this is like intuition or certain hypothesis. But what we often observe is for a sport such as tennis, when a player's height increase, the player has more advantage because the angle where and the player can hit the ball is better with the taller like body size. So the height, when it increases, will create some benefit for the player. But there's a certain point, the performance may go down if the height continues to increase. In case of tennis, if somebody is too high, too tall, the offset, the downside of that is this player may have a problem of lowering his body or her body if the other side is returning a slice ball, because literally it's just too tall and it's harder for a tall person to bend the knees, lower the body to return a slice. Also with the like extreme height, it could be a problem of the body's mass center is too high, so that the player could lose some stability or lose some balance as a result of extreme high. extreme height. So that's why we put the hypothesis or certain intuition that is maybe there's certain optimal height for sports such as tennis. Nowadays, if you observe the best players, they have a body height around 6'2". It's just like kind of phenomenon of the height is beneficial until it's too tall. And the speed is something else we can expect nonlinear effect, right? I kind of think that speed's contribution could be exponential. Think about this. If somebody runs so fast as a cheetah, or even at the speed of a sound, that player has huge advantage because that player can always get the ball and always all around the other players, and no other players can catch his speed. So if we keep increasing the speed while maintains everything else as constant, the speed contribution to the overall performance to the player can be exponential. Anyway, I just make two examples based on certain intuitions or certain hypotheses, trying to make the point that is the inputs, the features contribution to overall outcome could be nonlinear. So given the previous two pages, we get some kind of intuitions. First, the features have interactions. Secondly, the individual features contribution to overall outcome could be nonlinear. So if that's the case, when we have a lot of independent observable features, let's say if we have 50 of those, x1, x2, all the way to x50, then if we want to build a machine learning model using regression or some sort of conventional model, it's not an easy job because we cannot just simply plug in each features as they are. Because if we do that way, the model's performance may not be that good. So we need to somehow consider the interactions among the features. We need to somehow capture non-linearity of features. How we do that? We may derive further features based on those 50 directly observable features. We may handcraft certain curves as on previous page, trying to capture the non-linearity of features response or features impact on the outcome. And then we consider the interactions. If we just consider the two-way interactions with 50 input variables, we'll potentially talk about 50 times 50 divided by 2 over 1,000 interactions, possible interactions. If we consider three-way interactions, we'll talk about something like proportional to the a cubic of 50. That number becomes even larger. So as you can see, if we're dealing with a complex problem with a lot of observable inputs, crafting the response, nonlinear response, and then considering all the potential interactions can be a very, very challenging job to do. And so it becomes burdensome, could even become not feasible in some sense. And also when we handcraft the non-linearity or handcraft interactions, we actually are dealing with very specific solution to very specific problem kind of situation. Because for each problem we're dealing with, if we're dealing with tennis versus basketball, it could be different from another problem dealing with like hockey, or maybe dealing with driving a car, because every problem is different and the interactions across the variables for each problem is different. So if we need to handcraft features, that means we're not getting a generic solution that could be more desirable. Now think our brain again. Our brain do not have the two problems that we just mentioned, right? First, for our brain, we just pass in the directly observable inputs. Then brain will make processing and make the decision and learn. And we do not need to explicitly pass any derived features into our brain. That's number one. Number two is our brain also has the generic capability of learning as long as we keep feed new information into it. That means our brain do not need to us to really have certain very customized solutions to each new set of problems. Given that, we probably should have some kind of incentive to have a solution, have an algorithm which kind of mimic how our brain works. And that's where the neural network algorithm comes in. And this is another way to look at to understand the power of neural network. And one striking feature which is good with the neural net is with more data coming, the neural network, specifically the deep learning network, can keep improving. But for traditional methods, when there's more data are fed in, the performance just got flattened out. And here, this performance we means how good the model's predictions are. All right. So now let's move on to neural network. More specifically, we're talking about the artificial neural network, which is a digital mimic of the biological neural network. Again, myself by training is not anywhere near to the neuronology, and my knowledge about the biological neural network is very limited. And probably even today, no scientist can claim they fully understand the biological neural network either. But anyhow, the the artificial neural network, the idea originally was originated, created by actually somebody in the neurology field. So this is a digital representation, very simplified way of represent to mimic the biological neural network. And nowadays, for artificial neural networks, there are different structures, different hierarchies. Today, we're going to talk about the most basic one. It's called the feed-forward neural network. And here it is how it looks like. First of all, we have input layers, which will have directly observable inputs, such in our case of pictures for dogs. We may have colors, we may have like size, we may have shape, certain describable inputs, observable inputs, which pass to the hidden layers. Hidden layers by name it suggests they are hidden and they are doing certain operations which is so not so transparent to the outside world. Then finally we have the output layer, and which again is kind of generates certain output which becomes describable again. In our case, we say, oh, okay, this is a this is a the dog, right? That's our conclusion. So which again become describable and commutable. And so we early on we talked about neural net and deep learning network. Essentially, when we have more than one hidden layers, such kind of neural network is called a deep learning network. So the reason we call this kind of structure called the feed-forward neural network is the information only flows one way. The input layers information flows to the hidden layers. There's no go backward, just going forward. Input layer information consumed and becomes the data or the certain numbers on the hidden layers. Then this first hidden layers pass its information to second hidden layers and no go backward. And then finally, the second hidden layers in our case becomes its information is consumed and make the final output layer projection. So this is a very simple sample. Of course, the number of uh, layers, the number of nodes on the input layers or the hidden layers, and even the output layers could be different on each different cases. And something also worth mentioning, the terminology. And each circle here is called a node, or you could also call those kind of neurons for those in the middle layers, in the hidden layers. So this is a basic structure of the feed-forward neural network. So now the question is, the input layers, the inputs are measurable. And then how could we do the calculation? How can we process information in the hidden layers? Now let's just use one node as example. Okay, we just care about the first node, the top node in the middle of our hidden layer. Okay, let's ignore everything else. We know this hidden first node, the first neuron, top one in the first hidden layers are directly get information feed from 6 inputs in our case. And the inputs, when they come to this particular neuron, got weighted by weight, right? W and something as we see here. The subscript just give us no kind of idea to describe where it's coming from and which node neuron is linked to. Let's using this one. Let's use this one as example. And it's coming from the input layer. Let's call the layer 0, and coming to the first hidden layer, layer 1. And because this is from the first input, and we put the subscript of 1, so this have weight 0, 1, 1. And then another one is also coming from the input layer, layer 0, to the second to the first hidden layer 1, and this coming from the second input have W 0, 1, 2. Anyway, because we have 6 inputs and we should have 6 weights associated with each input, and all these inputs, all those weights apply to the first neuron. And this first neuron also has some kind of threshold value. We put it as B and 1, 1. And the subscript 1, 1 just indicates it's on the first hidden layer and it's the first node in the top node in the first hidden layer. Anyway, then we do the linear combination of B values and the input values and the weights. So this is very simple linear combinations of inputs, weights, and the B value threshold. And that gives us something called a Z11. And Z is really just a simple linear combination of a bunch of values. Then that's not the end. We will pass the Z value to an activation function like this. In this case, the Z value will become the X in the activation function, and correspondingly will read at whatever X location, the Z location, what is corresponding the vertical, the Y value, and that value will be returned going back to this node and this neuron, and which will be as the input to the next layer, to the nodes, the neurons to the next layer. The most basic form, the very, very commonly used activation function is just the sigmoid function or the logistic function, if you still remember from our earlier logistic regression section. And this is basically the sigmoid function, also known as logistic function. And if we know the value z as we calculated on previous page, we just plug into this simple transformation or activation function. And this is what we get. For if the z is between the value, let's say -5 to +5, and the corresponding transformed value will be between 0 and 1. So it's really the S-curve shape. And again, this is just one example which the activation function is sigmoid function. And there are actually different activation functions we can use, but in general, this is the setup, the framework. We pass the z value, which is based on the linear combinations of inputs, weights, and threshold, then go through certain nonlinear transformation, the activation function. So by doing that, we can get the value for the first neuron as we have looked through just now. And the notation will be the activation function's outcome using certain linear inputs, and for z11, right? Z is a linear inputs. The outcome of a linear combination. Similarly, if we also have weights, of course, will be different from what applied to the first neurons, and everything come to here. We can also have a certain z value z12 because this is a second node in the first hidden layer, and apply it to the activation function, and then have z13 plug into the activation function, and the z14 apply to the activation function. If we do this on each of the 4 nodes, neurons in the first hidden layers, we get those values. And now they will be the equivalent of I values in the very first layer, the input layers. Those will be values flow into the following hidden layers and nodes in those hidden layers. Of course, we'll have corresponding weights, and each hidden layers have its own threshold, like B value. Eventually, if we keep doing the propagation, like feed forward, feed input become this layers, and feed this layer's input to next layer, eventually the whole network will be kind of will be fed with the values one layer to another, and eventually the outcome which we are interested in is also the activation from the final Z33 in our particular case. Anyway, so that will be the final outcome that we can have here. One thing to point out is in reality, for each layer, you may apply different activation function. That means the activation function across different layers do not necessarily to be the same. All right, so we actually talk about this one. In this case, we only have one output, right? This is desirable for a case such as regression case, because we only want to predict a numerical variable from the whole process using certain inputs. And in some cases, if we're dealing with a classification question, like something like we look at early on, such as handwritten digits classification question. In this case, our output is not one single input. We actually may have a bunch of output nodes, right? Each of node represent 1, 2, 3, 4, 5, all the way to 9, because potentially the digit we need to classify into could be anything, any integer from 0 to 9. And in that case, we have 10 potential outputs, and the outcome from this output will be probability, how likely the outcome is on that digit. So the short story is, for regression, we only have one node in the output layer. In the classification question, we will have many neurons in the output layers. Eventually, what we do is for each output neuron, we have probability, and most cases, we take the maximum probability across all the different nodes on the output layer, and whatever the node associated with the maximum probability will be the final answer. For instance, if we want to know the hand-written digit is 0, 1, or all the way to 9, if we observe that the prediction suggesting that is the 2 has probability of 80%, of course, 80% is higher than any other potential probability you can get from other digits. So then our conclusion is, given 80% probability for the outcome is a digit or number 2, then the 2 will be the conclusion from the classification prediction case. Anyway, it covers what we want to cover today. And today we talk about some concepts associated with neural network, and then we talk about the structure of the feed-forward neural network. And we now just assume that we know the ways, we know the threshold, how we could push feed information layer by layer from the very beginning, input layers to the hidden layers, finally make the predictions. When we're doing this, we assume we already know the weights, we already know the thresholds which are suitable for each neurons. The question about how we determine the weights, how we determine the thresholds, that be the topic for our next session, because it relies on a certain technique called backpropagation. That's all for today.